I'm joined today on The Siliconomist by Mike Chieco, co-founder, CEO of FlyingWire, a startup that's building digital nervous systems. So first, thanks, Mike, for agreeing to be on one of our early guests. FlyingWire recently emerged from stealth. The core technology, I think, came out of Georgia Tech. Want to dig into that, where your co-founder developed early research that became the foundation for the company. So Mike, welcome. It's great to have you here. Thanks for coming on.
Thanks for having me. I'm excited to be here. And yeah, I think what we're building is pretty exciting.
Cool. Well, why don't you start by telling me more about that? What is FlyingWire building?
Yeah, so FlyingWire is like you mentioned, building the digital nervous system for the physical world. So the way Mike Filler and I view the world is we've spent the last 60 years improving the brains of a computer. Thinking about how do you integrate a circuit? How do you build an even better circuit? How do you put it all on a little piece of silicon? And what we ignored is, if we take the analogy one step further, the peripheral nervous system and how that peripheral nervous system actually integrates with the world. Now, we've heard of IoT, we've heard of digital twins, physical AI, all these things, but they're all fundamentally limited by the same economics of actually deploying hardware in the physical world. And the deployment of hardware is 80% of the cost of hardware in the world. It's not the silicon, it's the deployment, the installation. And so what FlyingWire is trying to do is take that cost down to zero. And we do that by integrating what we call integrated materials. We take traditional semiconductors, we singulate them into smaller pieces than anyone else in the world. And then we integrate them into everyday materials like tape, like drywall, like carbon fiber. So you're no longer installing hardware, you're just using the same primitives you'd use in the built world. They just happen to be instrumented this time instead.
So sensors out of everything, or sensors and tape that you can put on anything? How does that come into the world?
Yeah. So we start with tape and we start with sensors, like you mentioned. So our first product is what we call pixel tape or AI data tape. It is literally tape that you lay down, and wherever you lay it down, you get a dense understanding of the world. Think a sensor node every inch.
Yeah.
We're rapidly moving beyond just sensors and just tape into structures, into stickers, into all sorts of applicable types of materials, and beyond just sensing into full-on compute nodes. I think edge compute or little neural nets all the way at the edge of its piece of tape. And so you could instrument and analyze wherever you stick this piece of tape.
Nice.
Yeah. Our design inspiration is actually my 3-year-old daughter, who is really, really good at tape. And we figure if she can figure out tape, if she can figure out tape, then the engineers in the world might be able to figure it out too.
It's awesome. She's like a little network engineer, bringing all the sensors together.
Exactly. We'll have to get her some IT books to start reading. I think the easiest way to illustrate what we're building is just to show you. So this is our first product. Like I said, it's pixel tape. We build these integrated materials. Tape is the world's most ubiquitous material. It's something like a $30 billion a year industry today. And what we do is we embed hundreds and thousands of tiny little sensing nodes, and that's what you see here, the little gold dots, into tape. And in our mind, that drives deployment cost to zero. And what you do with this tape is wherever you stick it, you start to get a really dense understanding of the world. So no longer are you simulating, no longer are you running computational fluid dynamic analyses or finite element analyses. You're just sensing instead of simulating. The goal here is to drive deployment cost to zero, build proprietary data sets faster, more affordably, and more accurately than anyone else. It kind of move us to this world that's been promised for the last 30 years. IoT was supposed to be very transformative, and it has been transformative in some ways, but it has not reached the depths that we expect. And so, our core hypothesis is we're actually pretty hardware poor in the physical world, and we want to be hardware rich.
So Mike, something like this, like you mentioned stress sensors, I think earlier, and temperature and pressure. What kind of sensors can you put into this tape, and what kind of things are you sensing?
Yeah, so fundamentally, FlyingWire's innovation is the manufacturing process to make this tape. So what that means is any sensor that can exist on silicon today, or any sensor that can exist through a fab, can exist on this tape. That means pressure, strain, humidity, temperature, vibration, accelerometry, light or the presence or absence of light, all sorts of optical sensing. I think the one area we have not yet dove into that has a lot of promise, but we haven't had the time to dive into yet is chemical sensing. Just because the world of chemical sensing is heavily dependent on the chemical you want to sense. But we hope to get there sometime in the future.
So you can get all those onto this little bit of tape. It looks like they're like centimeters apart. So very dense set of data, run it up a pipe or run it up a bridge column, or where do you envision this going?
Yeah, so our first use case here is in the infrastructure that's powering a lot of the AI revolution today, which is data centers. So data centers today have a environmental sensing modality of kind of one sensor every 3 racks in a
Okay.
data center. And what we say is we should put this on every rack and get 48 times the amount of data. So this
Wow.
this GIF that you see here is our tape being installed today at a data center, and it is 52 sensors running down a rack, giving you temperature, humidity, and air pressure every inch. And so, what that enables you to do is really get a dense understanding of what is happening in the data center, and you move from this world of kind of very sparse data, very sparse understanding of what's going on, to effectively a computational fluid dynamic simulation of the air in the data center in real time. And so what we're seeing in our early pilots is that we can get 156 times the sensor density just by installing this tape for the
Mm-hmm.
same sensor or for the same install cost. And just like we've instrumented the digital world up the wazoo, so every pixel you and I look at is tracked. Every time we move our cursor, it's tracked. And the reason we do that is so we can get insights that no one else can get. That same density applied to the physical world leads to some really critical insights on cooling, on customer service, on how you run your data center that both helps the end user of the data center and the people running it to optimize their business.
So it looked like deployment was pretty easy. The last GIF had the guy just rolling a piece of tape right down the side of a door, and boom,
That's
that's
right.
it, right? And then when you think about them taking action on that, and specifically in data centers, turning things on and off, or how do you capture the value out of that? You've got this great understanding of where stuff is and where the temperature is, right? But
Yeah, so it's this is where it gets, you sort of have to bridge between the physical and the reality of the business that you're running. So in the data center context, 30% of the operating cost of a data center is just energy for cooling the place.
yeah, yeah,
And every kilowatt that you put towards cooling is both a kilowatt that is eventually wasted because it's just kind of floating into the air, or
yeah.
it's a kilowatt that you cannot sell as a data center operator. And
Hmm.
I'm sure as many of your listeners have heard, energy is the fundamental limitation. Power is the fundamental limitation that data centers are facing today. And so, for years there's been this concept of, oh, well, if we just decrease the cooling costs, everyone wins. If we just
Yeah,
decrease the amount of cooling, but the tension that exists is how do you do that in a safe way that guarantees that you're not going to uh, overload the data center or overload your customers' components or break something in the process?
yeah,
And so the way the data center industry has done it today is they've established industry standards. The industry organization is called ASHRAE. And they've
hmm,
said, if you cool at this level, then you'll be fine.
okay,
And what we say is, it's the 21st century. We don't have to have blanket standards like that. What we can
yeah,
do is sense, the actual physical limit is how hot is the data center getting at every point that matters. And so if you measure every point, then you can know with statistical certainty, I know for 99.5% confidence interval, based on the history for the last month of this data center, that I can lower the set point, meaning I can increase the temperature of the data center airflow and
yeah,
not have a bad impact on my business. And so I think that's what matters in the data center context, is how do I safely save money and
yeah,
safely free up energy for cooling? To date, it's all been done by blanket peanut butter assumptions.
yeah.
Tomorrow with
Pretty
Flying
thick
Wire,
roots
it's
are.
exactly. It's everything has been treated, in the aggregate. And what we're saying is you need to get specific. And
Yeah.
that's the sort of insight you can't get from traditional sensing today. John, I actually tried to go instrument a data center with existing sensors at this density because I was like, before I build this product, we should probably test this hypothesis. And I was buying sensors off of eBay because these sensors today cost $150. So if I wanted to put 50 of them on a rack, that's what, $30,000 worth of sensing on one rack. So I was buying them off of eBay. And then I was zip tying them to racks. And by the time I was done, God bless these folks who let me try this, the place looked like a hedgehog. And I'd spent 10 grand. And it's just,
Yeah.
it's not doable. You need a new paradigm to get there.
Well, so when I think of digital nervous system, right? Like I'm thinking some of the applications I threw out there earlier. We're talking about like you could put this on a wing, right? I think we've talked about that where you might be able to measure structural stress. You've got
Yeah.
also, we have aging infrastructure. You can sort of measure with greater certainty and model that better to that degree, right? And the idea of wearables, just something I can track my my broken ankle quicker for quicker recovery, something along those lines. But the data center is like a non-intuitive beachhead that I would have thought of in terms of where you kind of enter the market. What's the sequencing decision there? Like, why was it high ROI or a controlled environment, or why did you go to market there first?
Yeah, so I think I think you're right. Like wearables, infrastructure, aerospace, those are all possible stops on our roadmap.
Yeah.
Data centers provide a couple different things that help us get a foothold. And I think generally in deep tech and semiconductors, the thing you want to avoid is building something for years before getting out there and getting market testing. And
Yeah.
so data centers allowed us to do a couple things. Number one, it allowed us to test quickly because it's a pretty benign environment. I mean, we're talking temperatures that are room temperature and hotter, and but we're not talking hundreds or thousands of degrees.
No
It's
FDA
very
requirements and
no
no
FAA requirements. If you meet someone crazy enough, they'll let a stranger off the street come and zip tie stuff to their rack. It has
Nice. Well, yeah. You
data
promised
centers
me a
have
30% reduction on cost. That's a good trade-off,
exactly. Well, but this is the sort of thing you could never try on a bridge, right? Like, and I wouldn't want to from a public policy perspective. You don't want things being tested on a bridge. You want what you know is going to work on a bridge.
Yeah.
So it's a benign environment. It has a lot of power and comms already built into it. So the power and comms, which tend to be the biggest challenges of any sort of micro electronic component, is easier to handle. And it's an area that has a really high need right now.
Okay.
When we look at the data center industry, we sort of see an analogy to 1970s airlines, where it was a sleepier industry.
Mm-hmm.
And it was a very steady growth and pretty straightforward industry. And now data centers are getting demands that they never expected. The density of power, the requirements of these AI hyperscalers, like all of these things are stressing the system. And just like the 1970s airlines, they don't have the tools to deal with it yet. Yeah. And so we saw a real need there.
That's a great analogy. It seems like it's also a clear value prop for them. Like you don't have to take 2 or 3 steps to processing the data. It's like, we'll lower your heating costs and we'll make things more efficient for you. That's pretty straightforward. So
yeah. No,
cool.
We're pretty happy with it as a first step.
So we brushed up against how you manufacture this, and I don't want to dive too deep in anything that's proprietary, but as I understand it, you start in sort of like a traditional semiconductor fab run. It sounds like you're making MEMS, right? To do traditional sensors that you might have with MEMS. And then are those going on chiplets? Like, how do you get it to the tape?
So this is both my co-founder, Mike Feller, and I have a really strong belief that manufacturing process innovation is what actually changes the world. So if you look at the history of industrialization, and my apologies, we're both kind of professorial. He's actually a professor and I just play one on television.
That's okay. This is the place.
Yeah.
Yeah, that's fine.
If you look at the 1870s and the Bessemer steel process, you look at how we make aluminum today, and kind of the innovations that have happened in that industry. You look at the integrated circuit and semiconductor fabs, like all those process innovations have really changed the world. And what we saw is that the way we make semiconductors today in these billion-dollar fabs is unlike any other manufacturing process in the world. It's analogous, and your listenership will understand this. It's analogous to 3D printing a car. And we would never say from first principles, a great idea is to 3D print a car. Let's lay down a layer of rubber and then a layer of metal. Instead, what we do is we make tires in one factory, we make engines in another, we make seats in a third, and then we put them all together at the end. And so what Mike Feller's process does is it moves us from the traditional fab infrastructure where you produce lots of one thing on one chip to that kind of modular manufacturing process where what we do is we go to a traditional fab, we build traditional wafers, and on those wafers, we have what we call microchiplets. So think of tiny pieces of silicon, 50 to 100 microns in size, that do one thing really well. And then we singulate those off the wafer and turn them into an ink. And that ink can be squirted down, deposited, and mixed and matched with other components so that you can kind of modularize at the micro scale and then wire it up and embed it in materials like tape, like paper, like carbon fiber. Actually, Mike's original research was funded in part by the paper industry. And some of the coolest demonstrations of this tech that we have is actually electronics embedded in paper. So think about, note paper that can sense what you're doing or compute while you're writing.
Oh, that's really cool. Yeah.
Yeah. And so that process is incredibly flexible. It's once you produce the components, you can mix and match like a Lego set. And that's where we think there's a lot of opportunity for us is not just in this kind of data center application, but in being able to meet all of the applications that you mentioned earlier where they are without having to go through radical redevelopment expenses. So instead of having to rethink what the tape looks like, rethink the architecture, respin silicon, it's just a matter of what Lego blocks do aerospace companies need to instrument a wing versus what Lego blocks do data centers need.
It also looks like, I mean, again, watching the GIF of the guy putting the tape in the data center, and that's it. It seems like there's great potential to sort of retrofit existing infrastructure or existing equipment, right? Unlike some sensor solutions, you're not doing like a complete rebuild or building from scratch to get this on. You can start getting high density sensors in there, like today with a guy with a roll of tape.
Yeah, and I think that's the main barrier, frankly, to why we don't have more hardware in the world is like, let's use aerospace as an example. If you want to build an aircraft today, the wiring harness is one of the single most complicated parts of the entire aircraft. So a Boeing 737 has over 200 miles worth of wiring in it inside a, what is it, 350-foot plane? And so if you want to, for example, put a strain gauge in a certain place, it's not just getting to put the strain gauge there, it's wiring it into every other piece of wire that is existing in that plane.
Yeah.
And so to your point, how do you do this in a way that doesn't require you to rethink the entire design of the aircraft at once? And yes, it could very much be a retrofit. So, putting tape on a wing spar of a 727, that wing is overstressed. And how do you manage that? Like that's one great use case. But where we've seen some interest from the military is not just in like retrofitting, but also thinking about, if I have the same airframe, but I want to put a new mission set on there, I don't want to have to redesign the entire wiring harness. What if I could just slap the wiring harness on with a piece of tape and then rip it off for the next mission and put on a new piece of tape that does a whole new mission set?
Yeah.
And so that's
the reliability is there. That would be amazing, right? Yeah,
exactly.
Real easy swap out.
And so you're sort of separating, in a lot of ways, you're trying to separate the design process of wiring from the actual structural process of wiring. And you can't do it with everything. There will always be things you need to put into the structure itself.
Yeah.
But for sensing, for mission capabilities, for edge compute, we think it could be really powerful.
Wanted to shift over just to talk a little bit about tech transfer. I know you're really passionate about that, and we started off by saying like this originated in a lab at Georgia Tech. Underlying IP is from Georgia Tech. You licensed it from Georgia Tech. It sounds like you're through that part, and I know that can be just like a super challenging process to recognize the value of some technology that's there when it's sitting on the shelf, and then university technology transfer is notoriously kind of messy. There are these valuation gaps, right? And academic institution incentives are sometimes misaligned with maybe commercialization incentives. Where do you start? Like, how'd you find this technology and value it and realize it was something worth taking off the shelf? And how'd that happen?
Yeah, so it all starts with my co-founder, Mike Filler. So I think Mike is a very unique academic in that he not only enjoys finding novel new ways of doing things, but he wants those novel new ways to really make an impact in the world.
That's great. Yeah.
I think all too often academic research is targeted at very specific problems, and it can become a little bit insular. And what gets you rewards in academia tends to be problems that everyone finds interesting, are not always, sometimes they are, but are not always connected to real world challenges that can be immediately applied.
Yeah.
And so Mike developed this manufacturing process over 5 or 6 years and then actually tried to go and commercialize it himself. He has a very strong conviction on this can really change the world. And the way he approached it was, partnering with a place called SpecTech, run by Ben Reinhardt, to basically write a white paper on how could we, in a academic and environment, prove out the capabilities of this in such a way that the private sector will notice. And then the private sector can take over development. And I was fortunate enough to stumble across the paper that Mike and Ben wrote in 2021 or 2022 and read it and said, there's really something here. And to their credit, it was not written for an academic audience. It was written for a layperson's audience, because it was trying to get people, particularly philanthropists like Eric Schmidt or the Gates Foundation, excited about this possibility of micromodular electronics.
And so had the academic, again, these are like academics, right? Had they already kind of thought of the commercial applications and put numbers behind that at all or anything? Or was it still academic at that point?
It was still pretty academic. It was very much focused on how do you demonstrate technology, with the assumption being, and this I suppose holds true in semiconductors, if you build a smaller, cheaper, lower power semiconductor, then there will be a market for it.
Okay. Yeah. Yeah.
But to your point, I think the biggest challenge that Mike and I faced when we first started thinking about how do you commercialize this is, what the hell do you do with a manufacturing process technology? And we spent 4 to 5 months doing customer discovery, going to folks, going to VCs, going to people, everyone we thought we could talk to about this, and basically getting blank stares, being like, huh? You can do what? Why do I care about that?
Yeah.
And I remember the day really specifically. Mike and I were having guacamole and margaritas outside of the Tech Square office in Atlanta, when we sort of inverted the problem and said, what if we, instead of making this a manufacturing problem, we make this a product problem? And what's the simplest product we can think of? It's tape.
Yeah.
And the next day we walked into an office with a roll of tape and said, what if I could instrument your office just with this roll of tape? And the guy leaned in and said, huh? What do you mean? That sounds cool. Now that wasn't the end, but it was sort of the end of the beginning, in that even for something that should be obvious in terms of you can make semiconductors smaller, cheaper, faster, more power efficient, you have to make it accessible for folks with a product, and that's where the tape came from. So it was a 9 to 12 month process of customer discovery, kissing a lot of frogs, and I think that's there's a lot of programs out there that teach you that. iCore, there's many little accelerators, but the reality is you just got to stick with it for a long time before you can find kind of the niche where you can thrive.
Yeah, to do it for 4 months, it can seem like the longest of times. It can also seem like the shortest of times. Like I've heard people working on that kind of thing for a year or more. But still, it takes a lot of grit and determination and a lot of creativity to sit there and take that idea and think, how can I communicate the value of this, and how can I kind of think through customer solutions for customers that may not know that they even need something. That's a lot to do, all at once. Was that before you got the license settled up with Georgia or Georgia Tech, or was that after?
Yeah. So once we started to understand, Mike and I viewed this very much as like dating. So, finding a co-founder, founding a company with someone, that's not a small thing. You have to very much know who you're getting into bed with, and who you're going to sign up for the next 10 years of your life with. And so,
yeah, for sure,
we took it very slow and kind of used that customer discovery process as a way to feel each other out on like, hey, do I like working with Mike Filler? I had biases coming in as a commercial guy I had seen academics, talk a big game of, I want this out in the world. But then, when it came time to actually do it, they didn't like some of the compromises that come along the way. And vice versa. Every academic Mike had ever talked to had started a company had horror stories of MBAs or business people coming in and basically stealing ideas or taking away their thing.
Yeah, there's like a big trust barrier there for sure. And you're right, like everybody comes with their biases and motivations, if you will. So
yeah. And so once we got through that process and kind of decided, hey, we work well together, we complement each other. And, I think Mike is a truly rare academic in a lot of ways. But one thing that's fun is he's an academic who reads business books for fun, and I'm a business person who reads science books for fun. So we both have a lot of respect and understanding of each other's fields.
Kind of meet in the middle there. So your technology right now is still, it's at, what is it, TRL 4 or so? Is that right?
We're at
so you're not fully out of the lab yet. So how important is that ongoing relationship with the university and the lab support that you guys get?
It's critical. And that's what we realized early on, is that if we wanted to do this for any sort of appreciably raisable amount of money, we needed to do it at Georgia Tech, and we needed to do it with the support of Georgia Tech. So we're raising $5 million for our seed right now. I think if we were to do it without Georgia Tech support, we'd be raising a $50 million seed, just because of the amount of equipment and capital we would need to get there. And so we started the discussions with the Tech Transfer Office and the Office of Technology Licensing early. And I've had a very productive discussion over the last 7-8 months. But to your point, it's a hard process. It's frustrating. I think the incentives are, everyone is working in good faith. Everyone is working in the best intentions, but the incentives of the system are such that I think tech transfer offices often feel like they've gotten burned in the past or taken advantage of, and that's unfortunate. And so there's a lot of things that would not immediately seem commercializable, approvals that you need, different restrictions on what you can and cannot do with the technology, all sorts of constraints that they rightfully put on their technology, but that you have to really take the time to understand and go back and forth on to see, can you match what you want to do with the business with the restrictions that are on this kind of technology? And that's what takes time.
Yeah, it feels like, so oftentimes these discussions feel like especially when you're with an early technology that hasn't really been commercialized or made very far on the TRL level, that there's a little bit of overvaluing on the university side, because it's super valuable that the technology or the idea has kind of been birthed. There's still a long road that has to be kind of acknowledged to get it into the hands of a customer and get it even generating revenue. It's like a perilous road too. It's got technology and market risk kind of dumped all over it. So
yeah, I think that's fair. What I will say is, the one thing to keep in mind is just the tech transfer environment is shaped by its primary customer, which is biotech companies.
Okay.
And in biotech, often like the molecule is the product. So if your molecule can cure your diabetes, you don't need to do customer discovery. I mean, I'm simplifying here a little bit, but like,
point. Right.
There will be a buyer
in the sense that there's a buyer for a faster chip. There's a buyer for a cure for cancer. And you're right. And the assessment of risk is just kind of different there too, right? It's like, will it make it all the way out? There are still technical hurdles maybe, and there's still FDA approval, but people put a lot of effort into that. So
no, and that's right. And so it's just a different calculus. And so for semiconductors in particular, like I remember one of our milestone discussions we had with Georgia Tech was, well, you need to get to a product within 12 months. And I said, well, I can't spin silicon within 12 months.
Right.
So like it wasn't by any means malicious. It's just like, okay, let's talk about the actual milestones you have to hit as a semiconductor company. Like, I cannot even get an iteration of my product in 12 months. I wish I could. Yeah. If you could figure that out for me, that would save a lot of problems for me. But
it sounds like they were flexible about that, at least, right? Like that's good.
Yeah. No, and Georgia Tech has been a wonderful partner. I think there are many universities, to your point, that view the innovation as the product, and Georgia Tech recognizes that there is a lot more that has to go into it. And so they've made their terms commercial. They've been very flexible, and they've been a great partner to work with as we've brought this to market.
I feel like whenever we've talked before, you've mentioned, you're passionate about the fact that a lot of the technology still sits on the shelf, that there's a lot out there that doesn't get developed and brought out of universities. If having been through this process now, I think both on the sidelines and then also directly for FlyingWire, if you had this magic wand, how would you fix it? Like, what would it look like? If a system that worked, what would it look like?
Yeah.
From the entrepreneurs. Yeah.
I think first I would separate out biotech and everything else. Biotech is its own unique beast, and everything medical that touches the FDA should have its own unique process. The second thing I do is I'd create a safe note for tech transfer. Safe notes have revolutionized how startups get financed. It used to be that startups would burn $100,000 on lawyer fees before they even got their first check. Yeah. And I think the industry has collectively decided that's silly. We don't even know if there's a there yet. So let's sign a document that kind of pushes a lot of the major decisions to later, but allows you to move tech forward and allows you to even test the market. And I think you need something like that for tech transfer. At the same time, I think there needs to be a recognition on the part of the entrepreneurs that the universities have tremendous resources to bear and tremendous resources to bring. And it's really disheartening for the university when entrepreneurs come in and say, I know best, I know everything, I've done this before, and try to dictate terms in that fashion. So I think there needs to be a little bit of a meeting of the minds. And if I had a magic wand, what I would do is I would physically put the MBA programs in the engineering building of a major university like Georgia Tech, and not separate them and say, like, this is the goal. Yeah. And there is a tremendous amount of resource here. There's this whole trend in MBAs going out and buying small businesses today, whether it be like your HVAC contractor or your pest control company.
LinkedIn is full of that now.
Yeah. LinkedIn, if you hear one more person talking about search funds on LinkedIn, that's fine. Wonderful.
Yeah.
I think there is that same opportunity in technology. There's so much technology
Yeah.
sitting on the shelf. There's so much desire from the US government and from other institutions to commercialize it. And
Yeah.
as a commercial person, you have some really unique skills. And often that skill is just sitting in a room and chatting with 100 different people until you can figure out what the hell this is useful for.
Yeah. Figuring out how to make it useful to the customer for sure. Yeah.
Exactly. And that is really hard. It's not easy, but it's something you uniquely can do. And so I would encourage other, MBAs to look beyond the HVAC company, look beyond the reoccurring revenue and think like, what can actually really change the world here?
Well, I love the idea of the equivalent of a safe note for tech transfer, right? So, or for tech licensing, even if it's
Yeah.
it might look a little different than a safe note, but I'm imagining almost like a I know that some government labs will give you an exclusive license for a period if you meet milestones and without much
Yeah.
more. So it's like you get like essentially a free license for a certain period of time until you can reach a level of commercialization. And it does give you like the incentive, or at least the exclusivity gives the ability to work in a protected environment and kind of build up your commercial path. But it still
That's right.
still has its flaws. And I guess I feel like I read the other day the Department of War has made a new website for showing off their tech transfer as if that was, I don't think that's really the problem, but they feel that somebody's paying attention to that and somebody's trying to get more technology out the door. So that's good. But
Yeah.
I think it probably has more to do with the opportunity to get out there and commercialize.
Yeah. There is, if I could do my career over again, I would start it in this space rather than take 15 years to get to this point, because I think there is so much opportunity out there.
Yeah,
And there is a playbook and there's a way to think through this, and it's a lot of fun.
yeah,
And I think there's a unique opportunity for MBAs and for the business types to have a true impact on the world, because what changes the world is not fundamental science in many ways, it's the commercialization of fundamental science.
yeah.
And we're rich in fundamental science, but I think in the States we've lost a little bit of the plot on what is important to build in the States.
We're working on getting that back, but I agree. Like I think that's a big hurdle for us now. So and I agree. It would be great. I think it's a very valuable and noble thing to do when you hear people speak idealistically about capitalism. I think that's what you envision as somebody thinking of a new idea that makes everybody's life better, and then gets out to the market, right? Not necessarily hedge funds and SPACs, but actually
Yes,
helping people get technology deployed, like the Bessemer process or all the other technologies that have kind of come out there and made our lives infinitely better.
I agree.
Well, Mike, FlyingWire, Chieco, thank you so much for coming on and talking to us. If we want to learn more, where should we go, and how do we figure out more about keep track of what you're working on these days?
Yeah, reach out to me at Mike at flying or mchico at flyingwire.io.
Okay, I'll put that in the show notes.
Thank you. Yeah, reach out to me. We'll have a website that's coming soon. We've deliberately kind of kept it quiet to date, but we'll have a website coming soon. And follow me on LinkedIn, and you'll see more of the progress as we go. I write a Substack, kind of documenting our journey here, called Dispatches from the Frontier.
Yeah,
You'll learn about this and some other fun science stuff that's happening in my life. But I think it's a fun journey, regardless if you like semiconductors, you hate semiconductors, or you like tech transfer, hate tech transfer. It's always fun to follow along. So come on and join us.
for sure. I cannot wait to get my athletic tape and wrap up my ankle, which I damaged skiing. So I want the promise of faster repairs. Can't come fast enough. Thanks, Mike.
Anytime. I hope to bring that future to you soon.